Hi guys, welcome to another video. So I have my final exams of deep learning in about a week or so. So in this video, I'm trying to revise all my deep learning labs and solve all the coding questions and concepts related to it. So I thought the best way to learn anything is to try revising it and teaching it one by one by revising all the concepts and saying it out loud. So that's what I'm going to do in this video. So hope you get along and let's start revising. So the homework assignment that I'm going to start with is called music generation with recurrent neural networks. So as we solve and embark on this problem, let's understand the in depth look of recurrent neural networks and why they came into picture and why do we talk about it. So, yeah, there are traditional feed forward neural network where our network tries to learn info and features from the input images or patterns and it and the goal is to minimize loss over the back propagation and achieve the best result possible. So but those are the traditional feed forward neural networks are like independent events, and it treats all the inputs as an independent event. So suppose example, you are analyzing a sentence with feed forward neural network. It would only analyze the first word or the word that it's focused on right now. For example, the sentence is, "What did you eat today?" So it will just focus on the word eat or today, not the sentences or words that come before it. So what we want is the word. The model should learn all the sentences and generate the semantic meaning out of a sentence and derive an inference based on all the past words before it. So that the word doesn't really just remain a word but it understands the whole sentence. So RNNs were introduced to solve this problem of learning patterns over long time period or temporal info, and this is why they were uh, they introduced this problem of recurrent connection and have a element called memory in its architecture that tries to learn the network's past activity or input sentences past word. That's the advantage. Now many people would ask, why are they even powerful? So they have variable length input output, so they can process input of any sequence length, I'm sorry. They can process variable of any input length, and the parameters and weights are shared across all time steps. So the same weight is shared across all time steps, and it kind of reduces all the parameters and enables the model overall to generalize across different positions in the sequence. So if you talk about music generation, here with the help of RNNs, there will be parameter sharing, and the rules for music notation would be same at the first as well as at the end and somewhere in the middle as well. So now let's talk about the hidden state and recurrent mechanism. So a RNN has a recurrent layer as well as a hidden state. So RNNs have a loop, and it's conceptually easier to understand by unfolding it over the sequence of length. Each time step in the sequence from t time equal to 1 to time equal to t corresponds to a copy of same network cell. At each time step n, RNN takes two inputs and produces one output. The two inputs are the current input as well as the previous hidden state. So in music generation, the current output would be the current music character and the data point at the input. Previous hidden state would be the previous memory from the previous time step. So how is the new hidden state computed? It is it is a multiplication as well as addition in one single operation. There is a weight matrix WHH for the recurrent connection from hidden to hidden. So there is a weight matrix from hidden input to hidden output, and there is also weight matrix for input connection from input to the hidden layer. There is a bias vector, and there is f called nonlinear activation function. So then, as in any general machine learning equation, there is the equation called y equal to mx, y equal to wh plus b, which is like input into weight plus bias. So here similarly, the final output is derived from new hidden state, where why multiplied by ht plus w plus bias of y. So weight matrix from hidden to output connection, and there is output bias vector as well. So how do we train RNNs? There is a concept called back propagation through time. So training an RNN requires a special usage of backpropagation algorithm. It has forward pass, loss calculations, and backward pass. So forward pass, the input sequence is basically fed through a unified network, and the hidden state is calculated at every time step. The total loss is calculated as the sum of loss at each time step, and in the backward pass, the gradient or the error signal is propagated backward from time starting from final step to the first step. So that's how the weights and back propagation is done from the final step to the first step. So it consists of basically three process: forward pass, where basically input is fed through unfolded network and hidden state is calculated for each input. There is loss calculation. The total loss is calculated as sum of loss at each time step. Here, specifically, cross entropy loss for music character prediction. But there is also one other challenge of vanishing and exploding gradient. Here in the process, as you can see, the weight matrix is multiplied constantly during the backpropagation through time process, because it's once through every time step. So weight keeps on multiplying with each instance, and there are two major issues here. First is vanishing gradients. Here, if suppose the value of weight matrix at each time step WHH is really small, the gradients will shrink as they compute forward, and as they shrink exponentially as they compute backward. This means the network tends to forget all the necessary information from the earlier time steps, and weight updates from past events become negligible. This is why vanilla RNNs, recurrent neural networks, struggle to learn long term dependencies. This is one problem of vanishing gradient, where it tends to forget the features from earlier layers, and forgets important information. Second, and doesn't work with long term dependencies. Second problem is exploding gradients. Suppose if the value in weight matrix WHH is large, the gradients grow exponentially, and this leads to massive parameter updates, causing the model to become unstable or diverge. So, how do we solve this problem? So, this drawback of RNN is solved with two other architectures. One is named LSTM, long short term memory, and GRU, gated recurrent unit. The long short term memory is the most popular solution for learning long term dependencies. It has three gates: input, forget, and output to regulate the flow of information in and out for a separate cell state. This cell state acts as a highway of information, allowing it to pass through the info with minimal degradation, and remembers all the important informations over long-term time temporal time period. Speaking of another network called gated recurrent network, it uses two uh, main gates. One is update gate, other is reset gate. and it is a simpler to get variant of long short term memory. It merges the hidden state and cell state into a single vector. GRUs have fewer parameters and are computationally less expensive while achieving performance that is comparable to LSTM. So we'll try and work on this lab how music notation, the ABC music notation generally works, and what are like the key signatures and melodic phases. And we'll try to see LSTMs and GRU in this lab. This is also a lab from MIT Deep Learning Lab, so you could easily find code anywhere on the internet. But I'll try to implement it from scratch, and it will be basically a walkthrough side by side. Okay, let's get started. I hope you all can share my see my screen, and I'm gonna rename this lab to music generation using RNNs. So uh, we'll first talk about dependencies. So yeah, dependencies. So we need something called Comet ML for model development and training runs. So we need a Comet account, and so this is Comet account, and we're gonna see. I think I have already an API setup because I already performed this lab, but let me check it once again. Right. These were some experiments, and basically, you go here, you generate your own API key, and you can copy it from here. So now let's head back to our lab. Mm, yeah. So to get started, we'll start with all the library installation. We're gonna install Comet, pip install Comet ML, and dev null. Oh, I'm gonna start my own runtime type, set it to GPU, then run it all again. It's gonna take some time. Right. Okay. And now I'm gonna do here import Comet L Comet API key. Please enter your API key here. I'm gonna just copy mine. Um, Let me generate another one. Generate new API key. Okay, let me use this one. I'll delete the previous one. Okay. And then we'll import all the PyTorch library. Let's import torch. And then import torch.nn as nn, import torch.optim for optimizers as optim. Then we need to download and import MIT intro to deep learning package. So we're gonna pip install MIT deep learning quiet, then import MIT deep learning as MDL. We're gonna import all the remaining package, packages. So let's import numpy as np, import os, import time, import monk tools. I'm gonna import IPython. Sorry, it should be from IPython. Import display as IPython display from tqdm, import tqdm, and then from scipy.io. This is specifically to process the musical files. Import write apt get install abc notation of midi tmdt terminal 2025. Okay, let's run this. No module named MIT Deep Learning. Okay, let's see. I'm gonna run this part here. See if this will. Oh, it should be quiet. I'm gonna remove this from here. Right, let's go back. Okay, seems like it's installed. Now I'm gonna run this. While it's being installed, let's work on the forward cells. So here I'm gonna set let's see if I want to work with CPU, I'm gonna do that. Torch.device CUDA. Okay. If you wanna use GPU, just set instead of CUDA, type in CPU here. Okay, now let's talk about the data set. So here I'm gonna type data set songs in the ABC notation. So we'll download the data set. Songs equal to mdl.lab 1 load underscore training data, and then print one song. example song equal to song of 0. So getting the first song from the array of songs, from the data set of songs, and we'll print what's in it. And then let's see what we get. Name song is not defined. Oh, sorry, it should be songs. Yeah, so we found 817 songs in text, and this is like the notation. And I cannot understand it all, but it's something. So as you can see, this song is in ABC notation, and we need to convert it to an audio waveform and play it back again. So convert to audio file and listen to it. So we're gonna say mdl.lab1 dot play underscore song, then example song. Let's see what happens. I don't know if the audio is on here, but we'll check once. Yeah, let me set that up. Okay, now we see an output. Let's see if we can hear it. We can hear it. That's great. So one thing to remember is the music here, the notation of music here consists of notes being played plus song title plus key plus tempo, and here it consists of all these things here. So how do we basically differentiate or get real info from it? So we're gonna join our list of strings of songs into a single string consisting all the songs. So all the 817 songs are gonna concatenated into one song. So let's name a variable called songs underscore joined, and then this will be used to join this. We'll join all the songs. We'll find all the unique characters in the joined string. So vocab equal to sorted set string join, and we're gonna find the length of unique characters in the data set. So we can see there are 83 unique notations or ABC notation characters in the data set. Now we're gonna process the data set for the learning task. Okay. So we have RNN in the ABC notation, patterns, learning strategy, and using this RNN we want the model to generate or predict a new piece of another music based on this learned information. So what do we want? We want the most probable next character of music. So how will we do this? We will input a sequence of characters to the model to predict a specific output by following each character in each time step. I'm sorry. So RNNs maintain an internal state that depends on previously seen elements. So info octal about all the characters seen up to a given moment will be taken for final prediction. Now we want to do is we want to vectorize the text because machines cannot understand the ABC notation. So what we want to do is we want to convert those into numbers. So that is about creating a numerical representation of our text-based dataset. We will generate two lookup tables, one that maps characters to numbers, and second that maps numbers back to characters. So this is what we want to do. So now create a numerical representation text or vectorize it. So let's define a variable called char to idx where each character is mapped to another output for I and U numerate vocab. So each character in this join string, let's try to print vocab as well. Let's see what we get. Print vocab 83 unique characters. So you can see there are like 83 unique characters. So here we are trying to assign a number or convert into assign a number or map a number to each of these unique 83 characters. Okay, close the bracket here. And then we also want to create a mapping from indices to characters. So let's see, idx to char equal to, we're just gonna convert it into a array. Let me try to print both. Print char to idx. Let's see what we get. We can see each of that got assigned a number. Then let's also print idx to char. Yeah. So we created a mapping of all characters. Now let's do print. Gonna start. I'm gonna create a mapping for char, comma, and I'm gonna print all like pair of character and char to id. It's basically this. Let's see. Yeah, you can see this is mapped to 0, this is to 1, this is to 2. And now let's go and vectorize this song string. So what we want to do is write a function to convert all the songs string to a numeric representation by mapping character to indices. So let's define a function called def vectorize underscore string, which takes in a string, and wanna convert each character in the string to its corresponding index. Char to idx. So vectorized underscore output equal to np dot array char to idx. Let's map character to it. For char in string, and we're gonna return vectorized output, and then we're gonna print vectorized strong string. Now we're gonna look at how first part of text is mapped to integer representation. Okay, so let's do print. Characters mapped to int. Dot. We're gonna format representation of first 10 songs which are joined. So yeah, first 10, and then its vector version as well, vectorized songs. So first 10. Now we're gonna check that vectorized songs is an empty array or not. Asset is instance, sorry, not asset. And then if it's like that, then we say result should be an empty array. Okay, what's the error here? Repr takes. Okay, so here I think I missed a bracket. Yeah. Now let's see. Sorry, unmatched. PR songs joined. Vectorize. I think this one's extra. Yeah. Here we can see. So let's see. Songs join 10. So these are like the first 10 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters mapped to number 49, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, as we can see here, we mapped basically. Now we want to create training examples and targets for input and output. So we're gonna divide the text into example sequences to use during training. Each input sequence that we feed into RNN will contain a sequence underscore length characters from the text. We need to also define a target sequence for each input sequence, which will be used to predict the next character. For each input, the corresponding target will contain same length of text except shifted one character to the right. We will break the text into chunks of sequence underscore length plus 1. So suppose sequence underscore length is 4 and our text is hello, then our input sequence is hello and our target sequence is hello. So the last 4 words are mapped to the output of 5 words. So yeah. So we will use the batch method here to convert stream of character indices to sequence of desired size. Okay, good. So now let's create the batch definition. Batch definition to create training examples. So let's define a function called get underscore batch, which takes the vectorized songs. It takes the sequence length, input sequence length, as well as batch size. Now we want the length of vectorized songs string. So n equal to vectorized score songs dot shape of 0. Length is n minus 1, so that is why here we do the same. Now we're gonna randomly choose the starting indices for examples in the training batch. So idx, like our index, equal to np dot random dot choice. We're gonna do n minus our input sequence length, comma size. Now we will construct a list of input sequences for the training batch. So we're going to do input underscore batch equal to vectorized score songs. We're gonna run from I to I plus 1. Sorry, not from I to I plus sequence underscore length for I in IDX. Next, we're gonna construct a list of output sequences for the training batch. So we're trying to map input and output here. This is gonna be vectorized songs I plus 1 till I plus sequence plus length plus 1. So basically adding 1 to here because we are like trying to predict the next character. So that is why we are adding plus 1 to the input. Okay. Now what we want to do is we want to convert the list of numpy array to a single numpy array first. So let's convert this into an numpy array. So we're going to do input underscore np equal to np dot array input underscore batch, and similarly for output underscore batch also we did the same. Now convert the numpy array to a PyTorch tensor for fast processing. So we're gonna do x underscore batch equal to torch dot tensor input underscore np comma d type torch dot long. Similarly for y batch also we did the same. Now we will perform some functions to check if our batch is working properly or not. Perform some functions tests to see if batch function is working properly. Okay. Test arguments equal to vectorized songs 10, 2. So we are passing vectorized song sequence length 10 and batch size 2. Okay, let's see. X underscore batch comma y underscore batch is test args, and we're gonna write a assert function x underscore batch dot shape. This should have shape 2, 10. Not asset. Similarly, let's do for y batch as well. Assert y underscore batch dot shape. Yeah. If not this, then we're gonna print batch function is working properly. Okay. We first took out the len, then we chose a random starting and dice, convert list of input to training bags, added +1 to the output, converted into numpy array, converted that numpy array into a PyTorch tensor. Let's see. So yeah, it is working properly. So now we know for each of these vectors, each index is processed at a single time step. For example, for input at time step 0, it receives the index for the first character in the sequence and tries to predict the next character. Index of next character, not the index of next character. At the next time step, it does the same thing, but it has memory. But RNN considers the information at previous time step, like its updated state. Addition to the current input. Okay, now let's see x underscore batch comma y underscore batch equal to, we're gonna pass it to the get batch function, get batch. Let's try to write song sequence length 5, batch is 5. We're gonna do for I comma, we're gonna make a pair input id x comma target id x, sorry, get underscore id x in enumerate z x underscore batch का 0 comma y underscore batch is 0. We're gonna print step, like first three steps, like first 4 steps in the same format, and we're gonna print the input and the output of it. Here it should be print input, format input idx. Of this representation we want format targets underscore idx comma repr idx to care target id x one dot item. Okay, so let's see. At step 0 we have input of 62, input index 62, and the character is g, and the output should be 60, which is e. At step 1 our input is this one, which is e, and output is d. Step 2 our input is last one, d, and the output is b. So we are trying to map all of this. At step 3 the output is b and input is b and output is this dash. Similarly for step 4. So as you can see our sequence length is 5. Output is 1 2 3 4 5, but input is 0 1 2 3 4. Yeah. Now let's try and build the main RNN network. RNN model. define and train RNN on our ABC music dataset, and then use the train model to generate a new song. We will train our RNN using batches of song snippets from our ABC dataset, from a dataset which we generated in the previous section. The model is based off LSTM architecture to learn the long-term dependency. Works with long-term dependencies. Here we use a state vector to maintain information about the temporal relationships between consecutive characters. The final output of LSTM is then fed into a fully connected linear layer, NN dot, where we will output a soft max, which gives us the probability of each character, I think, over each character in the vocab, and then sample from this distribution to predict the next character. Okay. In the model of NN dot module, in the model, we have different layers. For example, NN dot embedding. What does this do? This basically is the input layer consisting of a trainable lookup table that maps numbers of each character to a vector with embedding underscore dim dimensions. We have nn.lstm. Oops, what happened? Yeah, .lstm, and it is basically our LSTM network with hidden state that learns all the info from the previous layer. We have nn.linear, which basically is the output layer with vocab underscore size outputs. Let's define the RNN model. So, oh, I just realized that I was not sharing the screen all this while. Oh my god. What? Give me a second, guys. Okay, what I'm gonna do is I'm gonna slowly like go through it again and share my output. I'm so sorry that I forgot to share my screen, but yes, this is what all I had coded. Um, yeah. Okay, so yeah, let me go through it once again. What I did is I installed all the necessary libraries, and then I got my songs in the ABC layer, like ABC notation. I downloaded the dataset from mdlab1.load underscore training data. I printed one song with all the characters. And as this is in character form, you would want to vectorize it to a numerical representation. I also converted this audio file and listened to it for now. So this is the function play song, and you can listen to it. Yeah. So next I joined our list of strings on the strong, like all the characters into one single string. So I joined all the songs and found all the unique characters in that string and found those are like 83. And this is the print vocab. You can see all the 83 unique characters. Now to map the input and output, we needed to process the dataset for learning task. So RNNs in the ABC notation patterns is used for learning, and we want to predict the piece of another music based on this information. So to do this, we needed to input a sequence of character to the model to predict a specified output by following each character. So this is done because they maintain an internal state that depends on previously seen element. So all the info is will be taken for final prediction. Then I created a numerical representation of a text-based dataset, generated two lookup tables called one that maps characters to numbers and second that maps numbers back to characters. So for each character and its index, I tried to print it, and then like converted into a vocab format as well, like sorry, array format as well. So here you can see there is this mapping. There is this numpy array consisting of all the characters. Then I tried to print the first 20 characters in this format with the numbers. Then I converted all the songs starting to a numerical representation by mapping it to the index. I created a function called vectorize string that takes in a string and converts each character to its corresponding index. So you can see here I did np.array char to index char for character in strings and return the numerical representation. That is the vectorized output of it. Then I try to look first 10 representation of character to its representation. So here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is mapped to numbers 49, 22, 13, 0, 45, and more. Then I created training example and target. So each input to the RNN will have sequence length characters from text and a target sequence for each input sequence. For example, if the text is broken into chunks of sequence length is 4, and our text is hello, then input sequence is hell, and prediction is hello. So we will use the batch method. I created the definition to make get batch. It takes in vectorized song, a sequence length, and a batch size. So first we find the length of songs string. So you can see the length is always n minus 1. So this is our shape and minus 1. Then I chose a randomly starting index for examples in the batch. So we do np dot random choice n minus sequence underscore length comma batch underscore size. Then I created a list of input sequence from vectorized songs. It runs from I to I plus sequence underscore length for I in IDX. And similarly, the output is just the next character from input. So that is like plus one here. Now to process further, we needed to convert this input batch and output batch into NumPy array first. So I used the function called np.array and then further converted the NumPy array into a PyTorch tensor using dtype torch.long and torch.tensor function. To see if it works properly, I sent a parameter and passed it to the function and used a simple print statement in case it works. For each of this vector, each index is processed at single time step. So RNN have a gate, so it has previous time step, updated state in addition to the current input. So I use this get batch function, passed vectorized song, sequence length 5 and batch size 1, and tried to print the step, the input and the expected output. So here you can see the connection. At step 0, the input is 62 index with character G and our expected output should be E, which is character 60. At step 1, this output becomes the input and forms like a connection. So input is E, output expected output is D. At step 2, this becomes the input, and similarly for all the steps, you can see that the previous output becomes the next input. Um, so I try to define and train a RNN on our ABC music dataset, and then use the train model to generate a new song. So now we will train our RNN using batches of song snippets which we generated in the previous section. The model is based out of LSTM architecture, which is like more improved version of RNN as it learns long-term dependencies. It has a state vector to maintain info about the temporal relationship. And then we use the final fully connected linear layer where we will output a softmax over each character like a probability. So there is going to be nn.embedding, nn.lstm, and nn.linear. Nn.embedding is the input layer consisting of lookup table. Nn.lstm is the hidden layer, like hidden state layer. And nn.linear is our output layer. So yeah, let's write further code. Now I will define a class called LSTM. So I'm gonna say define the RNN model. So let's make a class LSTM model and dot model. We're gonna do def underscore init. This is like a boilerplate initialize function self. It takes in vocab size, embedding dimensions, and hidden size. Then let's use super function for LSTM model, comma self init self dot hidden state equal hidden size equal to hidden size, and similarly self dot embedding equal to nn dot embedding takes vocab size and embedding dimension. Then we're going to do self dot lstm nn dot lstm, and it takes embedding dimension and hidden size. And then linear takes hidden size and vocab size. As you can see here, the input is vocab size embedding. Here the input is the output of this, like it is forming a connection, embedding them hidden size and then hidden size and vocab size. Okay, so let's see what all these layers do. LSTM like the layer 1 basically. I'm gonna add some comments here. I'll add a comment here. Layer 1 is LSTM with hidden size. No, sorry. It is basically an embedding layer to transform indices to dense vectors of a fixed embedding size. Next we have layer 2. This is LSTM with hidden size. Next we have layer 3. Input size is set to. Layer 3 is basically linear layer which is output size of LSTM layer. Now we are gonna make another definition called def init underscore hidden, and we're gonna do self comma batch underscore size comma device. Let's see. And here we want to initialize hidden state and cell state with zeros. So we are gonna return torch dot zeros 1 comma batch size. This one size comma self dot hidden underscore size to device. Similarly, torch dot zeros 1 comma batch size self hidden size to device. So we're gonna initialize this is the hidden size and this is the cell state with zeros. Let's define another function called zeros. Sorry, forward layer. Self x comma hidden state equal to none. return underscore state equal to false. X equal to self dot embedding X. If state is none, then state self hidden in it, batch size 1 device this. Then out, comma state self dot lstm x state. Out is I think this is wrong. Out dot permute 1, comma 0, comma 2. Out equal to self dot fully connected. Out return out if not return state else out state. So here in the forward thing, we need to reshape our basically the layer. LSTM expects input shape like sequence underscore length, comma batch size, comma input size. We need to reshape X from batch underscore size sequence underscore length, comma embedding underscore dimension 2 sequence underscore length, comma batch underscore size embedding dimensions. So this is why we need to reshape it. So we're gonna do X equal to X dot permute 102. If state is none, self init hidden batch state this. And then output needs to be reshaped back to this is not hidden state, it's hidden size. Okay, so this is what all we did. We defined the class, we defined the embedding layer, LSTM layer, fully connected layer, defined the init hidden state and cell state. We defined the forward layer, reshaped and shaped it again. Okay, now we have to instantiate the model. Build a simple model with default hyperparameters. Let's initialize vocab underscore size equal to length of vocab. Then let's do embedding dimensions equal to 256. Let's do hidden underscore size equal to 1024. Now we're gonna find batch size as 8. Let's do device equal to torch dot device CUDA if torch dot CUDA is underscore available else CPU Now we're gonna define the model variable, basically our LSTM model equal to LSTM model vocab underscore size, comma, embedding dimension, comma, then underscore size to device. Let's see. Why is okay? Yeah, I got the error. Should be defined. Now we're gonna print the summary of the model. Let's see. Print model. Name LSTM model is not defined. Oh, I did not run the previous cell. Module torch.nn has no attribute model. Module torch.nn has no attribute model. It's not model, it's module. I'm so sorry, guys. Okay, let's see. Now this works. Okay, so let's see. Our LSTM model consists of an embedding layer of 83 and 256. So embedding layer, this means vocab size is 83 and embedding dimensions is 256. Next is LSTM layer of 256 and 1024. So LSTM layer embedding dimension is 256, hidden size is 1024. And the last layer is input features like 1024 and output features is 80. So and bias equal to true. So we are gonna now test our RNN model. Test our RNN model. So it is always a good idea to run few simple checks before like testing our model, running our model. So I will do input shape and prediction shape check with some sample data. Test model with sample data. So let's do x comma y equal to get underscore batch. Vectorize songs. Let's do sequence length 100 and batch size 32. X to device, y dot to device, and let's do prediction equal to model. We'll pass our input x. We'll print input shape comma x dot shape. Yeah. Number, sequence length, and batch size. Output shape should be sequence length, batch size, and vocab size. What does it say? Module torch has no attribute zeros. What line is it referring to? Let me search zeros. I think I mentioned zeros somewhere instead of zeros. Yeah, here. Okay, so our input shape is sequence length and batch size. It should be batch size and sequence length, I feel. And this is gonna swap. And it's inside. Keep her check. Okay. So input is 32, 100, sequence length that size, and output is this 3283. So now we're gonna do predictions from untrained model. To get actual predictions from the model, we sample from the input distribution. We sample from the output distribution, which is defined by a torch dot softmax over our character vocabulary, because softmax always gives us probability. This will give us character indices. We are using a categorical distribution. To sample over example prediction. This gives us a prediction of the next character, specifically its index at each time step. Torch dot multinomial samples over a categorical distribution to generate predictions. So let's try and sample. We're gonna do sampled underscore indices torch dot multinomial. We're gonna do torch dot softmax red equal to 0. Okay, let's print it. I expected argument value. Oh, here one. So this is like sample from our entire output distribution 62, 45, 44, 43. But we now to decode it. We need to now decode this to see the text predicted by our untrained model. So let's decode it. We're gonna do print input line character representation dot join idx to char, because we are converting from indices to characters, so swapping it like indexes to character x of 0 um dot cpu. Okay, this looks good. Okay, यहाँ पे brackets. Okay, yeah. And then we're gonna print next char prediction representation sampled indices. Let's see. So here, this is our input character and this is our next character prediction for each. Output looks nonsensical as it is untrained. Now let's train the model. I don't know how long it will take, but we can try. Training the model. This is now a standard classification problem. Given the previous state of the RNN as well as the input at a given time step, we want to predict the class of the next character. That is to actually predict the next character. Okay. What kind of loss we should use? We should use cross entropy loss. Negative log likelihood. As it combines both log softmax and NLL negative log likelihood loss in a single class and accepts integer targets for categorical classification tasks. True target is our label and predicted target is our logics. So we will now define the loss function. Let's start. Cross underscore entropy equal to NN dot cross entropy loss. Then we're gonna make a definition compute underscore loss. It basically takes logits and labels as parameters. Input should be patch underscore size and sequence underscore length. And logits should be patch size, sequence length, and in addition to this, it should be vocab size. What should be our output? loss. Scalar cross entropy loss over batch and sequence length. So we will first batch the labels. So that shape of labels should be batch and well. As it flattens the label tensor. So we will do batched underscore labels equal to labels dot view minus 1. Next we will batch the logits. So that shape of logits should be batch multiplied by sequence length and vocab size. We reshape the logits to flatten the batch size and sequence length dimension while keeping vocab underscore size intact. So let's batched underscore logits equal to logits dot reshape and then -1 comma logits dot shape -1, and then we're also gonna compute the cross entropy loss using hash next character and prediction. Cross entropy loss expects n comma c logits and n labels where n equal to b into l, c equal to v. Okay, so we define our compute loss function. Now we're gonna compute the loss on the predictions from the untrained model earlier. Compute the loss using the next true. So we're going to do example underscore. We'll do it on the untrained model first. So loss equal to compute y comma pred. Let's see, where is our pred function before this? Pred. Let's see if we defined a variable called pred. Did we? Yeah, here pred is model of x, so basically the output shape. Then I'm gonna print f prediction shape Basically, batch size, sequence length, prediction shape. Okay, let's see if this works. Hmm, where is this coming from? Host softmax is not implemented for long. Okay, wait. Example batch loss dot mean item. Mm, mm, mm. We need to convert it into a floating point before passing it to the compute loss function. Okay, let's see. Will this work? Mm, no, not really. Mm, 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 mm. I'm gonna see. Oh, softmax is not implemented for long. Okay, should I remove this? Oh, wait. What the hell? What if? Okay, yeah, it's working now. So we can see the torch size prediction shape is 3283 and our loss is 4.42 or something. So now let's provide some hyperparameters. Define the hyperparameters. Okay, let's do vocab underscore size equal to length of model parameters params equal to dictionary training iterations. I'm gonna do 8 for batch size, and then sequence underscore length equal to 100. Learning rate 5v3. Hidden dimension 256. Hidden dimension, hidden size 1024. Okay, now let's make a checkpoint.
It's 2 o'clock.
os dot make dash system equal to true. Let's create a comet experiment now. We're gonna end any prior experiments that we did with comet before this. So let's do if experiment in locals experiment dot end. Then we can initiate the comet experiment for tracking. Oh, better. Now API key. Project name 6S191 underscore lab part. Now, I think this was never closed. What was never closed? Okay, experiment dot flush. Okay. Now we will define our optimizers. Define optimize duration training. Instantiate a new LSTM model for training using for created of. So we're going to do model equal to LSTM model cab underscore size comma params embedding dimension hidden size to device, and then we learning rate. So we're going to do optimizer Adam optimizer with the parameters, and parameter is learning rate. We'll define a new function called train underscore step, which takes an x and y, and we'll set the model to train. Set the model mode to train. So we're going to do model dot train. Zero gradients for every step. Optimizer dot zero grad. We're going to do forward pass. Handles the hidden state implicitly, and model initializes two zeros for the new batch. So we're going to do y underscore prediction equal to model, sending the input x. Now let's compute the loss. Loss equal to compute underscore loss y comma y underscore hat. Backward pass. Back propagate the loss dot backward clip gradients to prevent exploding gradients, and then dot else clip grad norm model dot parameters comma 5. Update the model parameters optimizer dot step. Now we're gonna return loss. Begin training. So let's make a variable called history, which will track all the training. Then we have something called plotter to mdl.util, periodic plotter, 2-second iteration and loss. Going to experiment equal to create experiment if h here if it exists for iteration in QDM range params numerical training iteration, grab a batch and propagate it through the network. Convert numpy array to PyTorch device to device x underscore batch. We're gonna take the training step. Now let's log the loss to the comet interface. Experiment.log underscore metric. Then we update the progress bar. Save the checkpoint if iter 100. Save the final trained model. Torch dot save checkpoint prefix experiment dot flush. Okay, here it should be dot not comma. So need to make a change train underscore step. Here it not should not be y hat. I think hat is okay. Here the error should have been resolved now. Okay, yeah. Do we have y paired anywhere? Because no. Okay. No. I think it is okay. Now we will run this cell. Let's see. I'm running this cell. Wanna see what happens. Comet warning. Experiment is live here. There is some error. Host softmax not implemented for long. Which cell is the error coming from? Okay, X batch or Y batch? Let me fix this once. Y had to float. So just to be safe here, it is recommended that we convert Y hat to float. Y underscore hat. Let's see if this works. I highly doubt, but okay. Okay, uploading 17 metrics and output messages. I don't see any graphs or so. And type object is not. Okay, why? Is it happening somewhere else? Okay, we need to use updated y hat as well, it seems. Okay, nothing's happening. I'm gonna stop this and write another cell. Can I just fix this? I need to run before runtime. Run before. So this is gonna run everything before. Let's wait till here. Mm-mm-mm. This was a complicated experiment, but let's see if we get our outputs or not. Now we need to next generate our next song. So meanwhile it runs, let's move on to the next cell. Start writing outputs. Uh, Generate music using RNN model. Use seed to get it started, as it needs to predict each successive character using our trained RNN model. RNN outputs a softmax over possible successive characters. I'm gonna refresh and see what happens. Reload site. Okay, I refreshed. Now I'm here. I'm gonna do from here. I'm gonna do run before. It started to run. Now let's do the prediction procedure. Initialize a seed start string and RNN state. Set the number of characters you want to generate. Using the start string RNN state, obtain the probability distribution over predicted character. Sample from multinomial index of the predicted character. This predicted is then used as next input to the model. Okay, did it create? Okay, 26. Now I'm gonna see if this works. Optimizer is not defined. What does it mean? Where did that cell go? Oh, yeah. Okay, yeah, this is already defined. Yeah. Mm-mm. Wait. What is the error here? I had comma y. Okay, let me try this. I'll change the step here. Mm. Meanwhile, this runs. I'm gonna do it again. Mhm. Restart session. Okay. At each time step, updated RNN state is fed back onto the model, and so now it has more context, making the next prediction. After predicting next character, updated RNN states are again fed back into the model, which is how it learns sequence dependencies in the data. As it gets more info from predictions. Okay, we can now see the graph. That's great. I think we fixed this issue. We can see the graph is like the loss slows down, like gets down, and the number of iterations is 2000, 3000 almost. And now let's generate music using RNN model. We'll initialize a seed start. We'll obtain start string and RNN state to obtain the probability distribution of expected character. We'll sample from multinomial distribution, and then at each time step the updated RNN is fed back into the model. So we'll generate prediction generated. So let's create a function, define generated text, which takes star string generation length. Let's give it temperature as well. The more the temperature, the more creative it is. So 0.0. Then we'll vectorize user list comprehension to map characters to the indices. So we'll do input underscore idx char to idx character c for c and start underscore string. Input idx needs to wrapped in an outer list for the batch dimension 1 comma sequence underscore length. So we're gonna do input underscore idx equal to torch dot tensor comma d type torch dot long to underscore device. We're gonna initialize the hidden state. State equal to model dot init underscore hidden input underscore idx dot size of 0 comma device. We'll use an empty string to store our results. Either empty string or list. We'll do text underscore generated. Let's make an empty list. We'll do tqdm dot underscore instances dot clear. Use the start string as the initial sequence of characters for I in pqdm range generation underscore length. Evaluate input and generate the next char predictions. we only feed the last character of current sequence for the next prediction. If this is the first step, input input underscore idx is the whole which will become single predicted character in subsequent steps. So we will do predictions, comma state equal to mod input underscore idx, comma -1 Yeah, I'm sorry, I got disconnected. My battery ran out, so I'm gonna start sharing again. Okay, so we were here, we were trying to predict and evaluate the model, generate next car prediction. So, predictions, comma state, model this. We're gonna remove the batch dimension, squeeze the length dimension, which is 1. Predictions equal to predictions dot squeeze apply temperature to the logits. Predictions equal to predictions temperature. Use a multinomial distribution to sample over the probabilities we take softmax to get probability and then sample one character. So we'll do input underscore idx equal to torch dot multinomial torch dot softmax predictions dimensions equal to -1, number of samples equal to 1. We'll reshape it equal to input x dot unsqueeze add the predicted generated text. Now we will use this model function above to generate ABC format text of length 1000. So we'll do generated underscore text. It starts with X. Yeah, okay. Let's see. LSTM object has no attribute hidden. Where is this coming from? Control F LSTM model. It does have init. What's the problem then? It also has init hidden. Oh, should I do init underscore underscore hidden? Let's see. ls. It's not supposed to be like this. Okay. Wow. Okay. I do have init hidden. I'm just gonna pass it once and see. Stay model. Get batch. Oh, okay. Got the error. So here in the init hidden function, here you can see. Let's see. see. Yeah, it's working now. Okay, so we can see this is the generated text, but it's like we cannot decode it as it's in the ABC format. Now let's play back this. So we're gonna write some more code. Play back generated underscore songs dl dot lab one dot extract underscore song snippet generated underscore text I in song and enumerate generated underscore songs synthesize waveform from a song waveform equal to mdl.lab1.song a underscore song if it's a valid song let's play it if waveform print generated song comma python display dot display waveform numeric underscore data np dot from buffer waveform dot data e16 wave dot file dot path f dot underscore I WAV. Right underscore. I'm gonna change the number here 8800. And then save your song to the commit interface. Experiment.log underscore asset file path. Okay. Which line? mdl.lab1. Oh, okay. Now I'm gonna pause. Five sounds and 5 songs in the text. Supported data type float. Should I do float 32? See, it's generating songs. Let's see if we can listen. Okay, now let's do one another thing. We'll try to do uh we'll also try to do print song. Let's see. Do songs in the text. Yeah. Okay, now let's have a look at comment as well. Uh, I'm gonna try to check and see if I can get any results in the comment account. Okay. I'm gonna run the entire thing once again, but I think it's working because we are able to successfully see the output. So let's run it all and see what happens. Run before. See, the graph is working. Now I wanna see if this, like, okay, what's happening. Okay, I think we're
It's 3 o'clock.
yeah, it was fun doing this. I was able to generate two songs. Okay. Thank you guys for watching this video. I'll share the notebook in one place and you can refer to that. I'll come up with another videos and another lab soon. But it was fun doing so. Thanks for joining.